The PAM PAS encoder and decoder components use the probabilistic amplitude shaping technique to lower the entropy of a PAM signal, which can be used for various reasons, such as lowering the average power of an optical signal or changing the baud rate under a constant bit rate. Under standard transmission, the PAM format transmits each symbol in a signal with equal probability. The bar chart on the right displays the fractional occurrences of each symbol transmitted within the PAM4 format. Each symbol is transmitted in equal proportions and is shown in the electrical eye diagram at the top right. Probabilistic amplitude shaping refers to the method in which each symbol is transmitted with different probabilities. In this technique, the high-powered symbols can be transmitted less frequently, and the low-powered symbols transmitted more frequently, which, among other reasons, can reduce the average power of the signal to lessen the nonlinear effects within the fiber. An electrical eye diagram of a shaped PAM4 signal can be seen at the top right. By shaping the constellation, the entropy of the signal is decreased. The bottom three figures display the electrical eye diagrams for PAM4 under various amounts of shaping, demonstrating no shaping, weak shaping, and strong shaping. Distribution matchers can be used to implement the probabilistic amplitude shaping technique. The CCDM encoder component in OptiSystem is used within the PAM PAS encoder to create code words with symbol occurrences determined through the Maxwell-Boltzmann distribution. The distribution matcher, with a cardinality matching the PAM format, maps a sequence of k bits to a code word of n symbols, where the entropy of the code word is approximately equal to the ratio of k to n when n is large. Displayed here are the PAM PAS encoder parameters. The decoder parameters are identical. The parameter levels defines the number of unique symbols within the output symbol sequence. For PAM4, levels should be equal to 4. The parameter PSN represents the number of symbols within each code word sequence output. The output sequence will be a multiple of PSN. Subsystem layout can select between different subsystem layouts. Select subsystem A to replicate the encoder described in this video. Parameters list defines which set of parameters are used to set up the encoder. Primary will allow setup through the parameter entropy. Entropy will hold the desired entropy of the encoder, which is estimated by the coding rate of the distribution matcher. As previously explained, this is more accurate for larger values of PSN. The encoder can also be set up using the parameter PSK rather than the entropy. For this parameter, the parameters list must be set to secondary. Then PSK holds the desired input bit sequence length for the encoder. This example displays the use of the PAM PAS sequence generator as a substitute for the PAM sequence generator using the PAM4 format. The upper setup shows the PAM sequence generator, which encodes an emery sequence with a uniform distribution of levels at a rate of 2 bits per symbol. The lower setup shows the PAM PAS sequence generator encoding for a rate of 1.75 bits per symbol. Here, we will use 4 levels to correspond with the PAM4 format, and use a code word with 512 symbols. We will also use the primary parameters list to set a desired entropy of 1.75. If we instead select the secondary parameters, we can use the parameter PSK instead. After calculating the simulation, we can look at the emery sequence visualizers to compare the symbol distribution. The system with the PAM PAS sequence generator transmitted a lower amount of higher powered symbols, and a larger amount of lower powered symbols than the standard PAM4 system.